He is part of the prestigious IBM Quantum team and is one of their most popular speakers and educators. Robert has been at IBM for 16 years in roles of increasing responsibility. He is also a QuizKit advocate achieved through testing certification and an IBM master inventor with over 160 patents. In his career, Robert has presented diverse workshops and lectures, as well as authored articles covering AI, bioinformatics, and quantum computing. He devotes much of his free time to philanthropy, contributing and volunteering to his community. Robert is dedicating 100% of the royalties from this book, Learn Quantum Computing with Python and IBM Quantum Experience, to one of his favorite charities, Doctors Without Borders. These funds will go help the many doctors, nurses, and other medical professionals and volunteers around the world where their main mission is to provide medical aid where it's needed most, and do so with their efforts remaining independent, neutral, and impartial. And finally, Robert has very kindly offered a discount code for attendees here. I've already pasted that in the chat room. So with that, Robert, I'll let you have it.
That's it. Perfect. Thank you, Mark. Hello, everybody. Good evening. Good afternoon, I guess, for some of you out west. So I'm going to start sharing my screen here because I think we have a couple hours, but I'm hoping it won't take the full 2 hours. I want to definitely open it up for some interaction and some question and answers here. So what I'm going to kind of cover here is, in essence, more or less a little bit from introductory, because for some of you joining who might not be familiar with quantum computing or the IBM Quantum Experience. So I'll cover some of the basics. At least I'm going to give you a tour of what's available, what we currently have, pretty much how things work on here. And then I'll switch over to the Python viewer. So for those of you that are a little bit more involved with quantum computing and particularly with Qiskit, can look at some of the features that we have. And of course, most of the notebooks and everything here, you'll see the content is either from the Open Quantum Qiskit community, and of course, some chapters from my book that, as Mark mentioned. So with that, let me get started here. And what I'll do is, for bandwidth, I will just adjust some stuff here. All right. So what we have here is, so generally when you come into the Quantum Experience, and it's you go simply to quantum-computing.ibm.com, which is the URL you have here. When you log in, and if you haven't logged in, you can register. It's completely free to join. There's no waiting. Just as soon as you log on, you're gonna land right here on this landing page, which is your welcome screen. And when you get here, you're pretty much already connected in the sense that you have now access to various different quantum computers. The Quantum Experience itself, as you can see, is a web app UI. Tailored in a sense for various things. One, obviously, for beginners, to actually get here and start learning about quantum. We have the composer, which I'll go through here, which allows you to do just clicking and dragging and creating these operations onto these qubits and running them on actual quantum computers. Which you see here on the right in the list of backends here, you can see there's quite a variety. We have different devices. So as you hover over, you can see there's different information you get from them, how many qubits this particular device has, the name, of course, which always starts with an IBM Q underscore. So here we have Bogota, Santiago, Rome, Athens, etc. And each device also lists the number of qubits and, of course, the quantum volume. Quantum volume, of course, being a metric that we use to measure the performance of these quantum computers. Because we've learned, of course, and we'll also learn here, that there's some effects that still occur with these near-term devices, that just having number of qubits isn't really enough to determine the performance. There's a lot of other things that go into it, such as effects around errors, noise, and all these other things, connectivity. So all that kind of computes into quantum volume. So each device pretty much has its own scale here. As you can see, we have quantum volume machines of 32, 16, 8, etc. Of course, you also have different configurations or topologies on these systems. So if we click on these, you'll see some detailed information about each device. In this particular case for Bogota, you can see this a 5-qubit machine. You can see the topology here. They're all qubits are connected in a linear fashion. So each qubit is connected to its adjacent one. So 1 is connected to 0 and 2, 2 to 1 and 3, et cetera, et cetera. You'll also notice that they have different colors around them, and those colors signify a couple of things. First of all, the ring around it, in other words, a qubit, the circles. For that particular qubit, those color coordinates, or those colors rather, map to these particular error rates. So you can see for single qubit error rates, they're very low here, which has a very light green or blue-green color, and it goes up here to a magenta with those with a higher error rate. So by looking at it visually, you can see that qubits 1 through 4 or a lot less error than the qubit 0. And this second scale looking here is looking at multi-qubit connections. So these are the connections between the qubits. And for this one, they use the CNOT gate, which we'll see what that is in a moment for those that don't know. But generally, it's a gate that connects two qubits together. And here you can see the qubits are connected by this little arrow in between the two. Any two of these qubits. So between 0 and 1, you have one, and between 1 and 2, you have this other one. And those two are color coded. So you have some differences there as far as the types of error rate that go between them. And of course, they're using the same color scheme that the single qubit, so that you can kind of see one version. You don't have to look at two different numbers and colors. So, and you can see here, like I mentioned, they're linearly connected. There's other devices, which I'll show you in a little bit, that have a different topology and how they're connected to each other. Down here, you can see a little bit of just a small snapshot of the information that's available on these devices. So, or the information from these devices. So you can see that because the number of qubits, how long were they since they were very first put online, how many number of shots, the maximum number of shots you can do on these devices, and we'll go over what that means in a bit. We try to calibrate these once a day. So this is last calibrate, you can see very early this morning. It gives you the information on quantum volume, and of course the basis gates. And basis gates is going to be important later on. We start looking at circuit analysis. And for that, it's because a lot of these gates that we're using, just as in classical systems, right, some gates are composed of various different basis gates, right? So these, for quantum, we have 3 basis gates, U1, U2, U3, that are for these that operate on single qubits. And then we have one gate, which is a multi-qubit gate, which is the control NOT. And of course, we have an ID gate, which is also a single gate, but it just really doesn't do anything. It's similar to a buffer gate, if you want to think about it from classical. And of course, the last one, here's the maximum circuits you can run on the device. And of course, we'll go over that here as well. So this just gives you pretty much a general overview of the different types of things you can see from each device that you would get access to. One thing here on the status on the left, you can see that the device is online, because sometimes they might be out for maintenance for whatever reason, upgrades, updates, etc. So you'll get that notification here. You'll also see how many jobs are in the queue ahead of you. So right now this device has 10 jobs in the queue waiting to get executed on the device. And then down here you have this little pulse icon here. And this is basically to determine that this device is enabled for pulse, which is the the ability to be able to program directly on the hardware. In other words, you defining the pulse width, the phase, the frequency, etc. So you can do that directly on the device on those particular components that we have connected to each quantum computer. So looking at the rest of these, like I mentioned, you have a lot of these different devices, different sizes. Also to note down here in the bottom, you also have access to a Cosm simulator. So this is different from simulator that you have loaded on your machine locally when you install Qiskit locally on your device. And by different, I mean it's on a different device, right? It's on the cloud. It's actually sitting on a Power 9 server. So it has a lot of resources available to it, a lot of memory, so it can compute a lot more things than you probably can locally with the resources you have, like for example, on a laptop. So you can see here, this is sort of maxed out to about 32 qubits that you can run on a simulator. So if you run out of resources or things are running too long on your local machine, you can actually run it on a simulator up here on the cloud. And this one is pretty much always online. And you can see the queue jobs run very quickly because it's all running on simulation here. So that's the hardware. And oh yeah, one thing I also wanted to show was the different topologies I mentioned. So the first one we saw, Bogota, you saw that was linear. This one here is in a sort of T formation. And of course, the difference here is you have a little bit more connectivity from a single qubit. From here, for example, from qubit 1, I can connect to 3 qubits rather than the linear form, where I'm only connected to 2 directly, that is, right? If I want to connect with more than 3, I could do that, but that's going to involve some information swapping or gate swapping here, which will add to the depth of this particular circuit that we're going to be creating. So having more connectivity in this sense is good, but sometimes obviously having too much connectivity might not always be ideal, particularly when you're looking at things like noise and errors, etc. So this just so you can get a good overview of the different types of machines that we have and what information you can get from there. So outside of the home screen here, so this is just the main dashboard when your landing page. If you come down a little bit here, The next option you have here are your results. So these are just jobs that you have currently running. So if we were to start running some executing some activity now, some circuits, and if they're in queue or they're currently running on the device, they'll show up here under the pending jobs. In other words, obviously they haven't been completed yet. And then you have these completed jobs, which are jobs that have already been run and completed, and you can go and look at the particular information or results from those jobs. So this gives you a really quick view of everything that's running currently on these particular machines. So, and the next one down here is a circuit composer. And this one is just, you can see is just a UI version of creating these circuits. And generally these are really good for ideally, particularly if you're trying to get started with circuit, generating quantum circuits yourself or building them out. One of the reasons obviously because there's not much programming. You can just click and drag and visualize a lot of the things. So I'm going to give you all a little tour here first before we start building anything, so you can get a handle and ideas to what everything is happening here. So across the top, you have obviously the different gates. So these are all the different gates that you can operate on a circuit. There's a list of the ones in the blue here are just X gates, ways you can operate on a particular single qubit or multi-qubit gates here as well. You have rotation or phase gates here. You have certain operations here, and I'll go over what some of these are. So I'm just going to give you a little overview for now. Then you have these rotation gates that rotate across different axes right here. So you have X, Y, Z. These basis gates that we mentioned earlier, U3, U2, and of course, some control rotation, which are multi-qubit gates here that we use for be able to control various different multiple qubits at the same time based on some conditions. And again, we're going to go over that here in a bit. Down here below that, you see your different quantum circuits itself, and you can see there's multiple different qubits here. Right now, by default, when you create one, you get automatically 3 qubits added to your circuit. And below here, you can see there's a classical connection here with classical bits here. You can catch or when you take a measurement, it grabs the results from those. So looking at here, and part of the reason why they called it a composer is not just to compose it, but you actually has that visualization of a sheet of music, and you can just in a sense compose. You drop your notes here and your operations, and it'll operate on that particular qubit and create this circuit that you'll render. So these, you got different qubits, you can eliminate them. So I can come out here and just say, I just want 2 qubits, or maybe I just want to have 1 qubit. Either way, you can control that directly here. If you want to add some, you can just click the plus, it automatically adds them for you. So you have a lot of different abilities to be able to control different things as you're building your circuit out. For now, we'll start with 1 qubit just to get an understanding as to what different operations you have and visualizations. So looking down here, speaking of visualizations, we have our 3 different ways of visualizing the sort of information from that particular qubit. On the first one, we have something called a Q sphere. And so just as it is, it's a bit of a quantum sphere or Qiskit sphere, however it is that you read on this. This particular one is a visual representation of the state of that particular qubit. So here, since we only have 1 qubit 0, we only have 1 state here. You can see it's 0 because when we initialize these qubits, they're always initialized to a ground state or the 0 state, right? So this is just how they're initially done. So since there's no operation on this, you can see from the results down here, the Q sphere, we have a probability 1, meaning that there's going to be a 100% probability in this case, probability being from 0 to 1. That if we take a measurement on this particular qubit, we're going to get a 0, which makes sense because we haven't done anything on this qubit yet. So if we were to just to run this and measure it, we're going to, and we run it 100 times, those 100 times we're going to read a 1. So this gives you some information about that here. Also, the other thing you'll notice here, it mentions the phase angle. And since if you picture the qubit as a sphere, right, you rotate it various different axes, right? So from the X, Y, or Z. So if to move from one state to the other, it's a rotation from one of these, if you want to think of it from a visual representation like this sphere here. So if you want to move, if we imagine the 0 state being the North Pole that we see here, and the 1 state being the South Pole, then to rotate it from 0 to 1, I just have to apply rotation, let's say a pi rotation around the X gate, around the X axis rather, and that will rotate it from 0 to 1. And of course, if I were to apply that same rotation again, twice, then the first time it would go from 0 to 1, and then on the second gate, it would go from 1 to 0 because it will just continue that same rotation. And the same, of course, will apply if I do a Y rotation or a Z rotation, it just spins it by a certain degree around the sphere. So when it's in the North Pole or South Pole, it's just absolute in that particular angle, 0 or 1. But now, if we want to put it in, so this, in a sense, we can say it represents the same information as a bit, a classical bit. So if it's in the north state here, the state 0, it's the same as bit 0 if we take a measurement. If it's in the south pole here or pointing down, it's going to be in the 1 state. We take a measurement, it's going to measure 1 back on a bit. The interesting thing comes in is when we're in a superposition, which is in a state, complex linear combination of 0 and 1. And by that meaning that it's going to be, it's this little dot you can see here, the edge is going to be somewhere else on this surface other than on the north axis or on the south pole or the north pole. So it's going to be anywhere here, whether on the surface on this front side or on the back side, if you think of this as a 3-dimensional sphere. So when if we just rotate it directly and I move it just to a superposition between 0 and 1, and I apply no rotation around the z-axis, then it's going to stay within this same phase, which is the 0 phase, right? So that initial phase that we're in. But once it's in a superposition, means somewhere here on the surface of the sphere, and I start applying rotations, then as I apply rotation, that latitude information is going to start passing in as a phase, right? So we're spinning around and applying various different phase rotations around it. And visually, that will change this color from a blue, which you could see from this little legend down in the bottom left. Blue is returns to meaning it's in phase, it's got 0. But if I rotate it out of phase by pi, it's going to have a red color to it. If I go pi over 2, it'll have a more of a magenta color, or 3 pi over 2, which will have a more of an amber yellow color to it. So this way, you'll get a more visual representation of what particular state your particular qubit is in. And we'll go over some examples of that here. Other information you can get also is a state vector. And this is just that it gives you the state information on this particular vector that we have, which can be applied. In this case, it's looking at one particular qubit. So it can either be, we weigh them or measure them out by amplitudes. So it's between 0 and 1. And the more qubits you have, the more this will spread out. And we'll get into that a little bit when we start adding more qubits here. And at the far end here for measurement probabilities, you get just that. It's what is the probability of measuring a particular value. As I mentioned here, when we have a qubit and we haven't done anything, it's at initial state of 0. So when we take a measurement and we read it from the quantum bit, the qubit down to the classical bit, it will read that same value, meaning it's pointing to North Pole. So this is where it is, it's in 0 state. If you were to rotate this, which you will in a minute, you get to see that we can actually change that probability based on the operations of that particular qubit. And how we determine the probability and the amplitude in the state vector is based on the operations we perform on that qubit. And we'll go into that in a second here. So the last thing I want to show you here is on the right. Right now, it's as soon as you log in, it starts off in this little docs tab here. And that basically is just if you want to get started on your own, you want to build your first circuit, you want to learn a little bit about quantum computing. So you have some links here that take you right to some documentation. You also have a guided tour, which gives you the tour pretty much a little bit more in depth, because I'm just kind of giving you a summary here because of the time that we have. But if you want to go a little more in depth, you can take a guided tour and it shows you all the different features and enhancements that we have in the IBM Q experience that can definitely help you get up to speed and learn a lot by just trying out a few things here. Other tabs that are up here is the code tab. So if you want to learn a programming while you're doing this, you can do that. So right now you can see this is the code it created in order to generate based on this particular circuit. So if we were to program this ourselves, this would be the code we use. And of course, we have different options of different codes we can use. So QISKit is our quantum information science kit. And that's basically what you're seeing here. It's a plugin, or rather it's a module you can add to Python on your Python code. So once you get it installed, you can run it right on Python along with your other experiments. We could have another option here of looking at the quantum assembly language, which is the QASM. And this is the open spec representation of what a quantum circuit would be in a sense here. So you can see it's using the version 2. And we're just, since all we've done so far is create a single quantum register and a classic register, that's what this is representing here. Now, in other words, this is all works in real time when you're creating. So if we were to grab something here, and let's say grabbing an Xgate and drop it on here, you can see it automatically updates the code. So you can see the code actually being written. And if we go back in the QASM as well, it does that too. So if we want to remove it, for example, now, get it and drag it off, it will then get rid of it and you'll see it removed from here. So let me see, actually, this is not on right now. So right now you can do various different things and you can watch the code update as it goes along. So this is really easy for you to learn pretty much how the code writes and how your gates pretty much operate on those. And from here, of course, once you got something going, you want to see it in the actual Jupyter notebook, you can launch this open in Quantum Lab, and this will open up the Quantum Lab and grab this code and directly run it onto your onto a Python notebook. So if you want to create something here and you actually want to run it on notebook and do some modifications there, you can do that here as well. And finally, here in the jobs is just that rather than going for you, this saves you the time of having to go back to this results view that we showed you earlier. You can just actually watch the jobs that you have running and see which ones are completed. You can click on it and it'll show you some results. So you can have all that information here as well. So with that, that's a bit of a tour here. So let's go a little bit into some actual creating circuits. So what you saw me do here just now is drop an X gate, right? And this is a NOT gate for those of you that sort of think of it as a classical representation of that similar gate. Is it, in essence, it rotates this along the x-axis of pi, so that you kind of see this here. So if you recall, it had the initial state of 0. We drop an X gate, it's now in the 1 state down here. So if I hover over, you can see it's in the state of 1. And if I look down here, you can see here in the amplitude, it now has an amplitude of 1 in that particular computational basis state of 1 now, as opposed to 0, what it had before. And the same thing here with the measurement probabilities, that is also set to 1 here. In fact, let me see if I can make this a little, so you can actually see some of these things here. There we go. And here for the state vector, it also gives you the state vector representation of that particular state for that qubit. So you can see various different things: a mathematical representation, visual representation, and of course the spherical representation here using the Q sphere. If we were to add now other things on here, so let's move this one off here. And give me a second, we cut that one out. And let me add here a Hadamard gate. So now I've done 2 things here. One, I've added another qubit. So now we have 2 qubits. So we have 2 different qubits that we're going to make some operations on. The first qubit 0, I applied a Hadamard gate. So this is putting it in superposition. What that means is that that particular qubit is now in a linear combination of 0 and 1. So in other words, if we take 100 measurements on this, I'm going to have 50% probability out of those 100 measurements get 50, and another 50 going to be probability of getting 1, 0 or 1 in this sense, right? In fact, let me get rid of this one here for a second, just so we can show you that here. So looking at the Q sphere, you can see now that the state of 0 is still blue. It still says I'm going to get some results in 0, but you can figure the probability, I'm now down to 0.5. So again, 50% probability of getting a 0. If I hover over the 1, I will see the same thing here, in that it is in a superposition. I also have the 50% probability there. With the state vector, you can see the same thing here. For the 0, I have a 1 over square root of 2, which is 0.707 amplitude, as well as the same thing for the 1 vector here. And this, of course, this array or this vector basically tells you what my state is of the 0, which is the first field, and then the 1, which is the second one in this array. So, and that kind of illustrates itself here as well. So you can see the state 0, I have an amplitude of 0.707. And here for the phase, for the first, I have an amplitude of 0.707 for 1 as well. And for measurements, again, same thing. And this one is just, if I get this value and square it, this gives me my measurement probabilities. And so squaring the amplitudes gives you your probabilities, which ends up being 50% 0, 50% 1. And again, this is what superposition is, in a sense that I now went from 1 state that I can now be representing this 1 qubit in 2 different states of 0 and 1. If I were to apply this Hadamard gate again, what this will do is bring us back to that initial state, which is 0, right? So that's what we have here now, which is the same as if we didn't apply the gates at all. So we have a state 0 here, probability of 1, state 0 here, probability of 1, state 0 here, probability of 100, and here the amplitude of 1. So what this basically shows us is that the gates are reversible in this aspect, right? Like we could be in a superposition, and if we apply another Hadamard gate, it brings us back down to that initial state, whatever that state was before. In this case, our initial state is 0, so we applied this here. But if our initial state, let's say, or rather initial state, the state before applying these Hadamard gates was 1, we'll see that if I apply 2 Hadamard gates, it's the same as, it's going to bring us back to that state we had before, right? So this is one thing you'll notice in a lot of, particularly when you start reading some papers and algorithms, you'll notice that a lot is start with putting everything its regular position. And the reason most of them do this is because sometimes when you have your superposition state, here you can take advantage of both states at the same time, right? If you want to if you want to search for something, or if you're trying to identify or trying to simulate or estimate some particular operations, you can do that here and take advantage of the parallelism, right? The quantum parallelism, in a sense of being able to operate on both 0 and 1 at the same time. And by doing that with some of these algorithms, when you apply this other Hadamard, you'll either get the result you expect, which would be in this case 0, or if there was some operation and it's something that you're searching for, you might get a different result back here. And that information is what gives us a little bit of an advantage over classical systems, because we can apply the quantum parallelism to do an operation, and then based on the results we get back, we can determine either based on the amplitude or the measurement probabilities that we get back, or some form, to be able to understand something about that circuit, whether it's we're searching for a value or if it's we're running some operations in different states. So that's one thing we can do, apply with these here. Another thing we can do, and I mentioned phase here. So if I take one of these gates out, so now we're in a superposition state, which we saw earlier. So right now, and one thing you notice is that they're both blue. So in other words, they're in the same phase. So if we were to apply a phase gate to something that's in a superposition, and again, think of this is that we're in a combination of the two. If I apply a rotation around one of the gates, let's say a Z gate here, I'm going to now also be in a not only superposition, but I'm moving the phase within that particular qubit. And here you can see it's determined that we did that by looking at the two qubits. Now we see qubit 0, or rather, I'm sorry, the qubit 0 is in the state, it's still in the probability state of equal superposition of 0.5, as well as state 1 is in 0.5. However, by looking at the colors, you can see that the phase is a little bit different. So if you look here in a state vector, we know that for the 0 state, we have an amplitude, the same amplitude of 0.707, but the phase angle here is 0, which is the way we had it before. But if we look at the 1 state, we have the same amplitude, but now we're out of a phase by an angle of pi, right? And that's because of that Z rotation. So what does that mean in essence here? If we look at it from a computational perspective, if you recall, when we had a Hadamard, if we're starting with a 0 state, if I apply a Hadamard, we had a superposition of 0, 1, which we have here right now. And if we applied another Hadamard on here, we saw that it returned back to the initial state of 0. But here, because we've had this particular phase shift, if we apply another Hadamard gate here and drop it, we'll see that our result is not 0, but actually 1 now. See that same thing here in a probability in a state 1. The probability there is 100% 1. The amplitude is 1. And you can see our vector here represents it, and we're finishing in that particular state. Right, so here was basically an illustration of where you can do some operation in there, and based on that operation will alter the results of what you normally would expect. And this is sort of the basis by a lot of these early algorithms that you see, like Deutsch-Jozsa, Simon's algorithm, that take advantage of these sort of phase alterations to be able to identify certain things, right? So this is where we sort of have that advantage, like I mentioned with classical, because with classic bits you need a lot of runs or a lot of operations to be able to determine some things. Here, by taking advantage of the quantum parallelism, you're able to apply phases and things like this to be able to extract extra results or extra information from that system without really applying too much extra information. Again, we're doing this with just 1 qubit. So that's for the single qubit. So we have superposition, and then we have here phase shifting within those. Another thing I want to definitely discuss here, which is another quantum operation, is that of entanglement. So we talked about 1 qubit, so we can operate, obviously, as I mentioned here, by using different gates. We can manipulate the qubit in a certain way to apply different computational movement around x-axis, y-axis, if you want to think of it that way. From a mathematical perspective, you're applying matrices, which is how these particular Hadamard gates, it's a 4x4 matrix. Apply that to a 2-to-1 vector, so that you can apply those to each particular qubit. So if I apply to connect these particular systems, though, in order to, if I have more than 1 qubit and I want to be able to entangle them so I can get more information and be able to apply different things, that's why we have these multi-qubit gates. For example, as I mentioned, some of the basis gates that we have here is that one of them is a control gate and a control X gate. So if we click and drag that down, we'll see that this has a particular different operation than a single gate, obviously, because it connects a couple of qubits. But one of the things it does is it does it in an interesting way, in a sense that it's called a control NOT gate because there's two connections here. You can see on the top, this is the control. So in other words, this is what enables or disables this particular gate. And what it enables is the target, in the sense, which is what's identified here by this little larger sphere here, and it has little crosshairs on it. And what that basically initiates, because this is a control X gate, is that based on this particular control, if it's a 1, it will enable this operation down here on the target qubit, which in this case, it's the second qubit. Which means that because of an X gate, that means that if when it's enabled or triggered, it's going to flip that or rotate that gate around the X axis, at least perform this particular operation. So in this case, when it's on, it's going to flip it from 0 to 1, or if it's a 1, it's going to flip it from 1 to 0. So by applying this gate here, when this Hadamard comes in, it's going to, as we know, it's going to be 50% of the time it's going to be 0, the other 50% of the time it's going to be 1, which means half the time this is going to flip this to a 0 when this is a 0, or rather not do anything when it's a 0, but when it's a 1, it's going to enable this gate and hence flip this from a 0 to a 1, or from a 1 to a 0, depending on what state it's in prior to this. But in either way, at the end, you're going to get, this is how you have the two qubits, in a sense, entangled. So what does that show us here? By looking at the Q-sphere now, we can see that we have, instead of a single state of 0, we have two states, and they're both initialized, and they both have a equal probability here of 0.5 and 0.5 for the other one, of being either state 0, 0, or if we look at the bottom here, we can be in a state 1, 1, and that's represented the same thing here in the state vector view. So we have a 0, 0 equal amplitude of 0.707, and of course for 1, 1, 0.707 as well. And this, of course, is how one of the advances or advantages of having things entangled, in a sense, because we can take now, we can leverage a lot of this information when we create these particular circuits. By entangling a lot of systems, we can then determine some information from one and pass that information, in a sense, somehow through these other qubits by having them entangled. So by here, for example, you can see you have two qubits set to 0, 0, another two qubits set to 1, 1. So what you'll have is, if I take a measurement on one qubit, let's say I just want to measure this one here, I will know that whatever measurement this particular qubit has from this particular state, I know that the other one, so if I measure here a 0, I know that this other qubit is going to be 0 without having to measure it. So I have some information there from that other qubit, but without having to actually touch it. Because as most of you might know, if you don't, what happens with qubits when you take a measurement is similar to collapsing a coin when it's spinning on a table. While it's spinning on a table, it's both heads and tails, but you won't really know what it is until you collapse it, in a sense, and measure it, and of course, or observe it. And then when you put your hand away from it to collapsing it, you can see it's either heads or tails. But you can't tell it to continue from that rotation and keep going, because once you collapse it, you have to just, in a sense, start spinning the coin again. So you have to start this again. But now if you have two qubits and they're entangled, this is similar to having two coins spinning on a table. And if you were to collapse one and see that it's heads, then in this sense, with they're entangled, that other coin, no matter whether you collapse it at the same time as the first one, or if you wait some time later and collapse it, it will also be set to that state of 1, or whatever, or heads or tails, or whatever that particular one was. So that's how the entanglement piece comes out. So this is basically the operations that these particular multi-gate systems have right now. Another thing also is, you can see that we can do these with the single gates, and if I apply another one here, I can apply a control NOT gate, or a Toffoli gate as it's referred to, and it pretty much has the same operation. You can see, except this time we have two control qubits, and then we have one single target. And of course, I can apply these as many times as I need to, depending on depending on my need, excuse me, for how many of these qubits I want to entangle to one particular target qubit. Some operations you'll see they'll have tens of not 20, 10 or 20 or 15, however many control qubits, or however many you need to control just that one qubit in order to get that operation to run. Excuse me. So from here, you can see the same thing here. By entangling these qubits together, we have the same thing. We have of course, you have 3 qubits, so we have either a probability of getting all zeros or all ones. So this can, of course, you can operate these as much as you need to, depending on the algorithm you're seeing. But the majority of the time, as you mentioned, when these things are run, this is the operation you apply within the set of Hadamars, and then you can obviously apply another set of Hadamars and get some results coming back, which of course will alter whatever it is that you need to work on. So this is the particular piece. So let me now do one thing before we switch over to the notebooks. Um, Once you have a circuit ready to go, you have it loaded on, you want to run it. So you drop some measurements. And again, measurements are just once you have that particular state, obviously we want to read it from you're running on a quantum system, but you want to read it back to a classical system. But of course, classical systems only know bits, right? They're binaries. So when you take a measurement of this combination of 0 and 1, you don't really read that back in a bit because bits only know one or the other. So when you do a measurement, when that's particular, depending on the circuit and what the results you get back, you're going to measure. If I run this one time, I'm going to get either 0, 0 or 1, 1 in this sense, in this case. If I wanted it 100 times, then I might get 50% of the time it will be 0, 0, and the other 50% of the time we want it more or less, right? So that's why when you run these operations, you run them a few times, and that's what we call shots, right? And those are just because, as I mentioned, these are probabilistic. One time it'll operate one way, the Hadamard will give you 0, the other time a Hadamard may give you a 1. So it's, again, because it's probability, you want to run these a few times. So when you want to run it on the system here, at the top right, you can see your run settings. You click on that, you get some options that come down. Now here, of course, when you see, you have a couple of different things you can select. First thing is your backends. So which particular device you want to run it on. So you can see it gives you little operations here, such as how many qubits and then the name of the device. And of course, at the bottom, you have the simulator that you can run it on. So for now, we'll just run it on the simulator just because I don't know if we have enough time to wait for the queue to go through. And here, of course, you have your shots. This means how many times you want to run this. If I run this one time, this is going to give me one of those two options. But for now, let's run it a few times. It's set to 1,000 by default. But of course, you can adjust that here with the arrows, or you can actually type in the particular value you want to run it. Either way, it doesn't matter. You can see it's already based on the device you select. It'll give you the maximum number of shots that you can run that particular circuit. So once we have all that set and set up here, then we come here and say run on IBM Quantum Simulator. So we'll do that. And you can see that creates now this pending job, and you can see the different states. It's pending, it's validating, it's running, and now it's complete. So once it's complete, we can click on this. It'll open up the view. And this is our results view. So we can see all the different things that happen. So you can see the type, it ran on composer, which provider we're running on, number of circuits, just one circuit, the time, and then it gives you all the different steps as when it go through, right? So how long was it take to transpile it, validate it, sitting in the queue, and then actually running it, and then obviously it's complete. Once you're completed, it gives you some more information. Obviously the backend you selected, how many shots, the status, how long it took, and when it was updated and run in this sense. And then you can see the results. So you can see here, just as we expected from the composer, we got approximately about a probability of about 50% of the state 0, 0, and the same probability, similar, about 50% of state 1, 1. So this gives us more or less the results we get back. If you scroll down here, you can actually see the circuit, all the different diagram, the code, and of course the Qiskit code as well. So it gives you all this information. And from here, like I mentioned before, you can select here to open it up in the Quantum Lab, and it'll take you right to it. So this is what you usually get back, when you can download it. If you want to be able to see it or put it on your device, you can delete it if you want as well. So this gives you all the results that you have in your particular run from running that particular composer. All right, so that's the composer, and what we'll do now is go into, how are we on time? Good. So we'll go now into the Quantum Lab. So Quantum Lab is, think of it as the next tier, or more of a deeper developer type of thing. In essence, it's a Qiskit, we used to call it the Qiskit notebooks, but it's literally just a notebook that's on the Jupyter notebook that's on the IBM Quantum Experience, and that particular notebook already has all the pre-installed modules and elements you'll need from Qiskit. So you have Terra, Air, Ignis, and Aqua, and all the different dependencies that it has, et cetera. It's already loaded in, so you don't have to worry about installing it locally on your device. So what I've done here is I've loaded a couple just to get us kind of started. And of course, we only had a couple hours, so rather than manually typing these in, I put these in ahead of time so you can see. So what we're going to show first is I want to give you just a little view of the qubit itself and the different ways you can visualize the quantum system. So first thing, when you create a quantum Jupyter notebook, it always starts off, particularly on the IBM Quantum Experience, it will generate this sort of boilerplate cell that pretty much just imports all of the most common used modules and functions that you need in order to create and run a quantum circuit. So you can see where it's importing the quantum circuit. the execute function that we use to execute the circuit, air, which we use for pulling in some of the simulators that we have, IBM Q, which we use down here, which helps us load our account. So when you actually run this on your device, whether locally or here on your Quantum Experience, you have an API token that you get from your when you log on, and that you get, and it loads it in here for you. So when you have this provider, that's basically used when you want to send some circuit up to run on an actual quantum device. So it'll check which quantum system you have access to. If you just log on for free, you'll have access to the free devices. If you're a member of the Q network, for example, you'll have access to obviously the premium devices, etc. So this all loads in that information for you. You can see it also loads in a lot of different nice tools and some visualization that'll help you kind of look at your results and analyze your circuit. So first step here we'll look at is just the qubit itself, how the different ways you can visualize it. So in the circuit composer, we saw a couple of different ways that you can see it. Obviously the results from the measurements, the state vector information, and of course the Q sphere. But there's also other ways you can look at things. So right here, for example, we're just going to grab our simple circuit, just like we did in the composer, a single qubit. It's in an initial state. We're not doing any operations on it. We're going to get a backend. We're going to grab the state vector simulator so that we can get the state vector information from it. And once we do that, we'll run it on that particular device. We'll execute it. So we'll grab our quantum circuit, which is what we created up here. It's a single qubit. And we'll run it on a state vector simulator. And then we want to get the results coming back. And once we get those results, then we want to be able to get the state vector information from that circuit. And that'll give us back our state vector results here. Once we have our state vector results, now we have that information. We can plot it anywhere we want. And there's various different ways you can plot it. So one of the ways you can do is looking at a block sphere. So you can see that, and you've seen these in probably many books and even in the Qiskit textbook as well. It's a very nice visual representation of the qubit here and in the form of a block sphere. So here you can see the various different axes that we have, as well as the different states. As I mentioned, pointing up 0 to the North Pole, it's the 0 state or the 0 ket. The South Pole, it's the 1 basis state or the 1 ket. And ket is basically the name of these notations that you see here around the North and the South Pole. So this is the one for qubit 0, which is the only one that we applied. Of course, it's initialized. We didn't do any operations on it. So it's pointing at the initial state, which is the 0 ket. And we did that by just passing in the state vector results here. We can, of course, do the same thing with what we saw earlier in the Q sphere, in the composer. We can get the same results here, which you can see it's in the top. It's in the North Pole. So hence it's in the 0 ket, 0 basis state, and it's red, indicating that it's in phase. It's in the 0 phase, as in there's no phase change on it. And also the thing is to look at the probability is also visually seen here, because by the size of the edge. In other words, it's at 100%, so it's very large here. But we're in a superposition, which you'll see later. You'll see that this will be half the size, and the other half will be the other size of that state. And of course, that'll alter depending on the different types of superposition states that you have. So here we're going to do the same circuit, except we're now going to actually make an operator similar to what we did earlier, applying an X gate here on that first circuit, on that first qubit rather. And then we're going to run the same thing we did before, run it on a state vector simulator, get the results, and then we're going to plot it on a Q sphere. And by doing that, you can see now our results, rather than being 0, we're down in the 1 state. And again, it's 100%, and we're in phase. So that's the first operation that we did in the circuit composer. Now, if we want to do something in the superposition, we can do the same thing here. We'll create a circuit, again, a single qubit, and this time we're applying this Hadamard gate. And the Hadamard gate is what puts the qubit into a superposition state. Once we do that, then again, we execute it and we get the results. And this time we're going to plot it first on a block sphere, so we can see what it looks like there. You can see the Hadamard, it brings it from the 0 state to right in here in between. This is what I mentioned, like we're just right in halfway between 0 and 1. So we're in a superposition state of 0 or 1. And since we're in the middle, that means that we're about 50% of 0 or 1 in this state. And of course, looking at it from a Q-sphere perspective gives you a similar representation, just slightly different in this sense that it's not really between 0 and 1. You just see the probability of 0 is represented here by the two edges. And the size, of course, is less than what we saw earlier up here. You can see in the 1 is 100% because it's a lot larger. Here it's a bit smaller, right? So because it's sharing that size now, so it's half of it is in 0 and the other half is in 1. If we had more states on here, we'd see that this would get even smaller and smaller. So this is basically based on the probability of getting these results coming back. In this case, right now, because we're in a state vector, we're looking at amplitudes here. All right, so that's just the visualization perspective. We'll now switch over here and talk a little bit about the quantum gates themselves. So in partially in the book, you'll have access to some of this source code. So you'll be able to get all that, all these little shortcuts in a sense to do this. But the reason I created this one was just so that we can get a lot of the information and not have to repeat a lot of the code. So what I've done here is created a same thing that we saw before. We want a state vector. But this I want to be able to execute the state vector, but I want to get some results back. And the results I want is the state vector results, the diagram on the circuit, and also the Q-sphere representation. So what I've done here is passing in an argument of a quantum circuit. And what I've done then is I grab the state vector simulator. And then after that, I execute that particular circuit that you pass in, get the results coming back. Then we get the state vector from that particular results from that. And then we grab that information. So first we have the state vector results, which is just that information we get back once we get to run the circuit. The next thing is you want to be able to draw what that circuit looks like. So we have the circuit draw parameter or variable that I'm creating. And of course, then we can draw the Q-sphere as well. So I wanted to get all these three. So what this thing is returning in that order is the state vector results, the circuit diagram, and the Q-sphere. The reason for this is that so now when we run these and we want to see, okay, how does this operation work? How does this gate work? How do these combination of gates work, et cetera? Right? We want to see what the state vector information is from that. You cannot just run that using one single code and it gives you back all those results. So going back to what we saw earlier, for the X gate, we run this now. So this gives us back. So if we read out the results, we'll see that this is the state vector results we get back. We see what that looks like on the circuit. So we have a circuit representation of that quantum circuit we generated. And of course, we can print out the Q-sphere information. So did that for the rest of the gates that we have here. So in the Y gate, you can see we do that the same thing here. It gives you the state vector information. We can see it's different in this sense. The image, obviously the circuit image on what that gate looks like. And of course, the Q-sphere representation here. So we do that for a lot of the rest of the gates, Hadamard gates, which we saw already. Hadamard with a phase rotation, which if you recall, we did this in the circuit composer. So you can see here we have the advent of being in superposition, but because of the phase rotation, we can now introduce something like negative numbers, which you can't do in classical systems. So by including that, we can now see that, and we're in superposition just like we were before, but just as we saw, this value here is now out of phase by pi, hence a different color. So now we know that we have equal probability by the size of the edges, but by the colors, we can determine that we are in not only the superposition, but we are out of phase here by pi on the one of the values here. So moving forward, we can see, and then of course I added a few others that we can go, and I won't go into too much detail, but like S gates, for example, same thing, gives you some information here on it, and phase and the S gate phase gate generally is the same thing, similar to a pi rotation, or rather a Z rotation, except where Z rotates it out of phase by pi, S rotates it out of phase by pi over 2. And you can see that by the results here. It's in green, so we're in the pi over 2 section here. So it's a quarter rotation if you think about it from the sphere. And then we can do the S dagger. And S dagger, in a sense, is the same rotation angle, just in the opposite direction. So if we look at that here, we have the Hadamard put in a position, then we run the S dagger. And that's shown here by the purple, or magenta, however you're seeing it. And this is a rotation of pi over 2, but you can see it's in the reverse direction, the negative direction. Right, so the S points it this way, and the S dagger rotates it the opposite direction. Same angle, just different direction. And we see the same thing here with T. T is this, pi over 4. So we're on here on the amber section that we can see in the color of the scheme here, as well as the T dagger, which is in the opposite direction. So it's pi over 4 in the reverse direction, which puts us in a bit of a magenta purple, which you see here. So those are different ways you can get that information back. And I'm going to go over a little bit more on all the other gates, but I won't dwell too much on these here. So another thing also is when you want to execute a circuit and actually get the results. So seeing the state information is just really executing it one time. because for a state, you just want the state of the information of that particular qubit or circuit. So the results coming back here, since we only have one qubit, we're only seeing the state information of one. If we had two qubits, we'd see 0001 or 11, and any other combinations that we have. So here, so that gives you that state information. Now, if you want to actually see the probability and the actual result that you get back, then we want to execute that circuit on a QASM simulator. So the above, we ran it on a state vector simulator. Here, I'm running it on the QASM simulator. And this basically will now introduce, putting measurements in and running this particular circuit a few times, and I mentioned that before by the number of shots. So we're going to do that and then get some results coming back. And this will be our probability results. So the first thing we want to do is get the simulator. So we're defining that to be the QASM simulator, which we want to use here. Then we're going to execute that circuit, and whatever circuit we're passing in the argument, we're going to run it on this simulator. And this time we're going to run the shots of 1024. And we're going to get back the results. And then just like we did before for the state vector, we want to read out the results in the array. We want to look at the circuit diagram of what we're running. And of course, we want to see the histogram this way as opposed to the Q-sphere. The histogram basically gives us our results in just that. What was the probability, or what were the times that a 0 came up versus how many times the 1 came up. And that's basically what we get returned here in this sense. So going back here now, what we're going to create here is the same circuit that we created in the circuit composer. We're going to have two qubits. So we have a quantum circuit here, QC, that's going to have two qubits. We're going to set the first qubit like we did before. We're going to put it in superposition, and it's going to be applying a Hadamard gate on that one. And then we're going to apply a C0 gate, control NOT gate over between 0 and 1. And here we're specifying the control as the first argument. So that means I'm going to apply the control on the first qubit and the target on the second qubit, or second argument, which will be here in the second qubit, which is 1. These are 0-based indexed. So this gives me the source and the target, and that's how it's going to do it. And then I want to put a measurement on all the circuits. I want to put measure everything. I don't have to do all, but this is just a quick way to do it. And once I do that, then I want to execute this using that method we created earlier, and that'll give us our results. So from running this first time, our results came back similar to when we ran it on a composer. 00 came up 525 times out of the times we ran it, and 11 came up 499 times, which pretty much maps to almost about 50%. Image gives us our circuit diagram, so that's pretty much what we drew. You can see we have our two qubits. The first one is in Hadamard and superposition, and here's the other one is in a single a quantum entanglement between the two qubits. And over here we have the two measurements that we applied. I said measure all. And by adding the measure, if you use the measure all, it automatically adds this barrier, which is just a way to separate your circuit from what it added the measurements from. That's all. And you can see it's mapped from 0 to 0. You can see the index. This means that qubit 0 is going to take a measurement and write it to qubit 0 or bit 0. Qubit 1 is when it gets measured, it's going to write the results to qubit 1. By default, when you're using the measure all, it's just going to apply it 1 to 1. But if I wanted to move this to, let's say, qubit 2, or rather bit 2, and I want to run qubit 1 and have the results to bit number 5, I can do that here as well and just do that programmatically. So this just does it when you want a simple way to do it, but if you want to be specific, you can do that here as well. So this draws out the circuit, and of course the last part here is a histogram, and this just grabs the results we got back and applies it in a histogram. So you can see from 00, we're at 0.513 and 11.487. I ran these two separate times, that's how you're getting these different numbers, but basically they would be the same numbers we get back over here. So that's those, and of course for multi-qubit gates, besides the control now, we have this CCX gate, which is that 3-qubit gate that we had. So to apply that, you do that very simple as well. We create our 3-qubit circuit. We have a control NOT gate here, and this is the same thing here. The control gates are the first two values, first two parameters. So I'm making my control 0 and 1, and I want to make my target is the third value, the last value, which will be the third qubit. And then we'll do the same thing here, run it. This time we're running it on a support vector because I want to see the support vector information on this. So you can see the result gives you that information here because we're doing 3 qubits. So now we have 8 possible states, and that's what you're seeing here. And since we're in the initial state, only the first one is enabled. Everything else is 0, right? So that's which makes sense. We haven't done any operations on this. What does this look like? You can see that here, which is the same gate that we drew up in the other diagram. And this is what it looks like. This is what it looks like as far as a gate when we create the gate. But now, one thing I want you to keep note, and this is one of the things that we could start going into the actual hardware, looking at hardware, is that if you remember all the systems that we have some basis gates. We had a U1, U2, U3, and those apply to the different rotations around that particular qubit. And then we have a multi-qubit gate, but we only had one. We have a control X gate or a CX gate. So as a basis gate, there is no Toffoli gate. We don't have a 3-qubit gate that's just out, that just works out of the box in this sense, right? So we have to actually compose this by using multiple ways of those gates. Similar to classic systems, you would use a NAND gate, an XOR gate, an AND gate to be able to create these other gates that we have. So the same way here, if we get this particular circuit that we have and we decompose it, and by that I mean break it down to those gates that are used in order to create this particular operation, you can see that it's composed of a Hadamard and T gates and multiple control NOT gates. So all these gates operating on these 3 qubits are what you need in order to create this effect. So on those 3 qubits. So even though you see one gate, it's really 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, about 15 gates here, right? So this is the reason I mentioned this is because this is where you start thinking, well, I have a two control NOT gates. Why am I getting some errors or it's getting noisy? It's only 2 gates. When you think about it, it's actually multiple gates. And if you apply 2 of these, then you got to get another set of these gates on here again too, right? So this, of course, increases the gate depth or the circuit depth of your operation because of all these gates that you need in order to create and compose this one gate operation that you're creating here. And of course, this will vary because if you have this is a control X gate. If you have a control Z gate, you might have different ways of permutations of creating these particular composing that particular gate. So using this decompose helps you get a good understanding and a real feel as to how deep your circuit is and how large your quantum volume you'll need in this case. Because if you have very short coherence time on some of these qubits, you're going to start seeing a lot of effects of noise very early, and that's going to not have very good values in your circuit results, right? So another thing here, we also added was swap gates, and this is just swapping information. So here you can see we have a gate, it's 0, 0, and here we apply an X gate on the second qubit. So this would, if we measure this right here, it would be in a state 1, 0, but because we have a swap here, we should be in a state 0, 1, right? Because we're swapping information. That's basically what the swap gate does. It just swaps the information here. And when we take a look at that, and if we go down to the measurements, well, you kind of see it here as well too. The gate 0, 1, the state 0, 1. And that's where we are, probably because of that's where we are. It was 1, 0, we swapped it, so now it's 0, 1, and that's what we have. And again, to read this, it's sort of a tilt your head. So 0, 1, so the qubit 0 is the rightmost position, and the qubit 1, and they start growing towards the left, right? So it's just like classical bits. Bit 0 is to the far right, and then you start increasing the number indexes over. So it's the same here. All right, so let me see. So these are the gates. And now we'll go into circuit monitoring and optimization. So now we're going a little deeper here with our circuit. So in the first 2 sections, we talked about qubits, the gates that operate on them, and of course, some of these gates that we have that are composed of multiple gates. And you need all these gates in order to be able to represent, for example, that Toffoli gate, that 3-qubit gate. And of course, if you have a 4-qubit gate or a 5-qubit gate, again, you're going to need just as many gates in order to create and compose that particular operation. So with all of these gates, and of course, you're just applying that, and on top of that, your algorithm, you're going to want to be able to monitor your circuits and optimize them as much as you can. So here we're going to take a look at how different ways you can do that, which also comes from the different features that are available with Qiskit, Terra, and Air and Aqua, and Ignis rather. So one thing we'll take a look at here, and let me actually run this so you can actually see it. So I'll run this one, and when that's done here. So the first thing we're going to look here and see is something called a job watcher. So this is a nice little widget that I like to have, particularly when I'm running multiple jobs on on different back-end quantum systems. What it does is a widget that you'll see pop up here in a minute on the back end that allows you to keep track of all the different systems and circuits you have running. So if you remember, we looked at the results view, we'd have to go back and look at the results in a table or in that particular view up here. But if you don't want to have to leave your circuit every time to do that, it's a good time to use this job watcher, because you can see it just popped up here. If we expand this, this will list out those particular jobs and a lot of information about them. So you'll see here, if we were running something now, you'll see the job ID, you'll see which backend it's running on or about to run on, the status of that particular thing. Is it in queue? Is it waiting? If it's in the queue, then to see what position are you in, how far back in the queue is this particular circuit in waiting on, and any messages come in, successful, or maybe there was an error, etc. So if I have multiple jobs running, I can always just expand this out, take a look and say, okay, did anything finish? If it did, I can click on it on the job ID, and it'll take me right to that particular job when it's done. So it's a nice little widget to have. If you have multiple jobs running and you want to clear it, of course, you can clear it from here. But it's just a really good widget to have, and it's a little bit out of the way here, so you don't have to have it open and blocking your code. So I can run some code here, and if I want to just check in every once in a while, I can just come here, take a look, and then come back and keep working. So it's a good little widget to have. So I like to usually have that running right away. And of course, after a while, if you don't want it, you can obviously disable it by running this particular piece. So this is just a good way to kind of keep an eye on your jobs while you're working. Another thing also is, as you saw, some of these devices have a queue. Some of them have a lot, there's jobs waiting for them, et cetera. They might not be busy, and some of them are simulators. Some of them have different size of qubits, et cetera. So there's, so to look and search for what's the most optimal device you want to run it on, there's a lot of ways you can do that. And one of the nice features that came out on Qiskit was this ability to find the least busy device, because obviously you want to run yours as soon as possible. So using the least busy allows you to be able to query out of the backends that you have available. So I'm using the provider. I can get a list of all the backend devices I have. Of those, I want to grab the least busy device that's available. So I can do that using this function. And then what that'll do is that'll assign a backend to me that's not busy at all. But besides that, as you saw, there's some devices that have 5 qubits, some have 16 qubits. There's one that has just 1 qubit, and there's the simulators. So depending on the circuit I want to run, some device that's not busy might not be the optimal device. So for example, if I have a 10 qubit circuit that I want to run, if the least busy device is a 1 qubit or a 5 qubit machine, that's not going to be good for me, because I'm going to get an error saying I'm running a circuit that has too many qubits on what this particular device needs. So with that, I can apply filters. And by using these filters, I could then specify, okay, of all the least busy devices, I want it to follow this particular criteria. And I can specify this criteria on pretty much any conditions that I have available. So for example, from the backend itself, I can say, okay, give me a backend system that has the number of qubits is at least greater than or equal to 2. Right? So if I'm running a 3 qubit, for example, if I'm running that 3 qubit system I want to make sure that I have at least the number of qubits in order to run this. So this will give me that information. If I want to make sure I want to run it on an actual device and not a simulator, then I could say, and I also don't want it to be a simulator. So eliminate any simulators, because more than likely the simulator is going to be the least busy, because those run really quick and there's rarely a queue. And of course, maybe I want to see, okay, which is the one that has an operational is true. I don't want a backend device that's in maintenance. So I'll make sure that it's true. And of course, I can apply as many other things as I want, other conditions I want to run. But for here, it's pretty much basic. So when I run this, I get a backend device, and this particular one, when I ran this earlier, it gave me this IBM Q_RNs as the least busy at that time. Once you get that device, you can view the backend results from it. And it'll give you details just like what we saw here, the number of qubits. So I can get the number of qubits on that available on the device, maybe how many maximum number of shots. So some devices have different numbers for the maximum, what you can maximally run on it, shots or experiments. So instead of having to wait and check to see what that device is, I can do that programmatically. So instead of just saying shots equals 8,000, if I know there's a device that gives me maximum shots of 10,000 and I always want to run the maximum, I would just apply this to say shots equals whatever backend max shots and run it on that. Same thing here with experiments, right? So all those information, you get that back, and you can just apply that value to your executable code, for example. And so that's some of the various different things that you can get in the back end. Of course, in fact, let me do this real quick and run these just to show you the visualization of these pieces here. Because when you're looking at some of this information, there might be some other things you're looking for. So if you're looking at maybe mitigating noise, or you want to find out what the coherence time is on a particular device, and you want to measure those kind of things, or identify, or at least have a configuration information from it to track when you're running it, you can do that by applying a lot of these different backend configuration values that are available. And in fact, here, let me just go back up. So I actually ran this so we can see this. So when we got this, I ran this just now. So right now, our least busy device is IBM Q Athens. And so when I have that device, if I want to view backend details, I could just run backend after it's been assigned. And you can see here, we get a lot of information similar to what we saw in that little widget in the beginning on the dashboard. But here you can see we get information such as quantum volume, whether it's operational, of course, the basis gates that are available, the max shots, max experiments, a lot of information here from that particular device. The coupling map, how are the qubits connected? So you can get all this information from the configuration. So if part of your experiment, you want to find out some of this information, whether you're running it on a circuit or if you're running maybe something on the pulse, you can do that here. It gives you a lot of the properties on the qubits as well. So you can see the frequencies on each particular qubit, how they're tuned, the T1 and T2 times. This is the relaxation and dephasing time, and we'll get into that in the next notebook. The gate errors for U1, U2, U3. These are those basis gates that we have, and what the readout errors are, etc. Right? And you can see the multi-qubit errors as well. The control X between 0 and 1, between 1 and 0, between 1 and 2, between 2 and 1. So it's each direction, right? So it gives you all that information. You can get a visualization of the error map, right? So you can see here what the readout errors are, and you can see here very similar to what we saw in the widget that pops out on our backend systems. You can see this also shows you the connectivity. This one here is linear, and it also gives you the color scheme on it, so you can see which ones are the clean versus which ones are a little bit noisy, based on the error rates and connectivity between them. So this gives you a lot of that information. And of course, like I mentioned before, once you have that backend pulled in, then you can pull out those information that we got in the configuration. You can pull those values out directly here as you need it. If you want to get a view of all the provider that you have available to you, you can do that as well in one view. So you can see here all visually. I can get a sort of a bird's eye view of all the different backends, how they're configured. You can see these are all linear, and here's ones that are not. This is sort of in that T shape that we saw earlier. So you can see all the systems. You can see the 15 qubit device here we have from Melbourne. And of course, you can see all the different configurations and topologies, but also information. Are they the least busy? Are they operational? What's the average T1 and T2 time? So there's a lot of this information we can get from various different ways, either individually from a device or just from this way, a quick overview as to see what's available. So now we're able to monitor the backend systems. We're able to monitor, how your jobs are running, whether they're in a queue, et cetera. But now we want to be able to optimize the circuits themselves, right? So when we have all this information about the backend systems, how can we apply it in a way where we can kind of optimize what we're getting back, what is actually working, and what can actually get done here. So let me actually run these. Actually, let me just do a quick run on most of these. So let's look up here. So let's start off with first grabbing two different backend systems, just to kind of see how optimization and the hardware work hand in hand in this sense. So you can see here, the first backend system I'm pulling in is called Santiago. So I'm just calling that one specifically. And here's the information on that. You can see it's a linear connectivity between all the qubits. It's got a quantum volume of 32, and it's operational, et cetera, et cetera. And I also pulled down a very different one. So here's our Melbourne, our 15 qubit system. So you can see here the different qubits. We have 15 qubits there. It's got a quantum volume of 8, and it's also operational, et cetera. So now I have two different backend systems we're going to run this experiment on. So first we want to do is we want to run a experiment that we can actually test and see how it works. So as you saw when we created a composer, we applied a Hadamard, and then we entangled them with all the other qubits. So here's what we're doing, the same thing. We have a qubit. The first qubit 0 is going to be in a Hadamard. We're applying Hadamard, so it's in superposition, and then we're connecting it, entangling it with the other three qubits rather. So we have a 4-qubit system circuit, and all of them are entangled together, right? And when we look at this and we say, okay, show me what this looks like now on this particular backend, how will this go? we can do that using this transpiler. Now, transpiler is different from using the execute in a sense. Transpiler just says, all right, how am I mapping this circuit and how it's generated onto that particular backend device? So here you can see we're transpiling this circuit and applying it to the configuration, in a sense, that we have for Santiago, right? One thing we're doing, and this is where the optimization comes in, we're setting the optimization level to 0. So you have different optimization levels, and this is basically how do you optimize the performance of your backend system. And there's different levels. You have optimization from level 0 up to level 3, and each level pertains to a different degree of optimizers and that you can apply to your particular circuit when it's getting transpiled. And level 0 being the lowest, meaning this means do not apply any optimization whatsoever. Whatever I'm mapping, if I say qubit 0, I want this on qubit 0 and I want this on qubit 1, it's going to listen to what I'm saying. So in other words, here I'm saying everything is mapped off qubit 0. So we have a header mar, and then we're entangling everything together. And I want 0 to be the header mar, and I want it to connect to qubit 1 first, then qubit 2, then qubit 3. And this is the configuration I want. It will do that. And you can see that how it's written here. So it's applying qubit 0, 1, 2, and 3, right? So that's exactly how it's measured, and that's how it's, so the header mar is going to apply here, and these are how we're connecting it. So one thing to notice, first is you can see the depth is 10. And depth means how many operations are we running there at each time cycle, right? So here, if we look at this, our depth is 4, right? 1, 2, 3, 4. We have 4 operations, running at the same time here. So the reason we have 10 here all of a sudden is because this particular backend is now doing a lot of different, remember, swapping, because gate, for example, here we have qubit 0 is because we're connecting it to qubit 3 directly here. But by looking at the topology, we can see that qubit 0 is not connected directly to qubit 3, and qubit 0 isn't connected directly to qubit 2. So in order to make this operation and this operation work, it means that somewhere along the line, we have to do some swapping of information. So there's going to be some gate swaps happening, which means this value is going to move here in order to get this to work. By adding those extra swaps and extra gates, obviously we're increasing the depth. That's why we have a circuit depth of 10. And that's basically what we're seeing here, right? That this is literally adding some extra gates to be able to create these particular connections. So even though control X gates are basis gates and they're there, when we want to make certain operations that don't connect to each other, then we have to add more gates, and hence our circuit is now deeper than it normally would be. If we look at the same thing here for Melbourne, we did the same thing, except we set the optimization level here to 0. So by doing that, it's doing the same thing. We have a linear set, 0, 1, 2, 3. And the depth here also is 10. And the reason is, of course, because it's linear, we have to do gate swapping on top of that. So we should have, even though we should have a gate of 4, a depth of 4, we only have 3. Now, if I apply the high optimization level now to these circuits, to these transpiled circuits. So here I'm going to optimization level 3, meaning optimize it as much as you can. When we do that to Santiago, if we come down here, we can see we still have a depth of 10, mainly because we're still linear. Nothing's changed. The connectivities are still not direct, so we have to do some gate swapping. However, notice now that the order of which of these qubits I'm calling qubit 0 has changed. It was this one, but now we're actually using qubit 3 is now qubit 0 in this sense, right? So you can see it's going 0, 1, 2, 3. And even though it's linear and our depth is the same, the reason it did the swap is for other reasons, other optimization. Remember, we're at optimization level 3, which means there's a lot of other things that it's looking at. For example, maybe this particular connection, we need to have longer coherence time on this particular qubit than the other qubits, et cetera. So it's looking, qubit 3 in this sense might be a cleaner qubit, meaning it has a better, it's got a lower error rate. And since this is the furthest one away and doesn't really get used, it might have a slightly lower error rate here as well. So they changed the direction because it just optimized it at that level. Even though the connectivity is still linear and we still have a depth of 10, compared to the other one, we'll probably have less noise here because this has been optimized that way. However, now looking at Melbourne, which had a larger number of qubits and more connectivity, if we set that to an optimization level of 3, we'll see a difference here now. So you can see the big difference is we have a depth of 4, which is exactly the same number of depth that we have in our circuit, which means that there's no swapping needed. Why? Because if we look at the topology of this thing, it's set up here in a way where our qubit 0, which you can see is right here in the middle, is now connected directly to 1, directly to 2, and directly to 3, which if you recall back up here in our circuit, let me go back up, is exactly what we have mapped, right? Qubit 0 is Hadamard, it's connected to qubit 2, qubit 3, and qubit 4, or qubit 3. So that's what we're seeing here, right? So the optimizer not only minimized the depth, but it also selected, I mean, it could have picked any one of these to connect here, but it picked these because this is probably the most optimal with respect to the qubits themselves, the coherence time of the qubits, right? The low error rates. Maybe these are a little bit noisy, so it might, after some time, you might get introduction of noise, even though they're connected directly. There's going to be there's some preference or optimization by running it on these particular 4 qubits. So this optimization is done, of course, under the covers by something that's called a pass manager, which is basically, it manages all these different passes. And these passes are these sort of code way of looking at the back end system, right? So it looks at these parameters that we saw here earlier, these configurations and the noise and the basis gates and how the connectivity between the qubits, the coupling maps like this, to know exactly, okay, you know, how are these things connected and which is the optimal way to do this. So rather than you having to figure this out, how to do that, there are optimizations and passes and pass managers that manage these passes to determine what's the most optimal one. And these, of course, being, you know, the code being open source, you yourself can go down there and come up with your own optimization pass and even a pass manager, because you may have 4 passes that are being used for this level, but what order they're being used can also be determined by the pass manager, which you yourself can also code up and create yourself. So that I wanted to get in here as well, so you can get an idea, at least on the various different ways of optimizing. So it's not just create a circuit and run it on your system. This just kind of gives you a little insight as to what's going on under the covers, under that execute call that's going on, that when a code is being transpiled, that things like this are going on to be able to optimize your circuit and your results, obviously. And of course, the last thing here on visualizations is this sort of a DAG drawer. So if you want to see what this looks, your circuit looks like with respect to a little a different design, different view, you can see here by this graph, you can see just pretty much how they're connected. All your qubits here in the initial state of 0 in the green, and then these light blue are the operations you're applying. So you can see from qubit 0, we're going to apply an H gate first, Hadamard gate. And then with qubit 1, we're connecting both of them via a control X gate. And then after that, we're getting qubit 0, we're going to connect that with qubit 2 via control X gate, and then qubit 0 with qubit 3 via control X gate. And then from there, we're reading the measurements, which you can see here. Qubit 0 is going to be read to Q0, Q1 to Q1, Q2 to Q2 to 3, and then Q3 to Q3. And then those will come out on the basis, rather in the classical bits. So those are your results that you can see here. Okay. So this is circuit optimization and monitoring. So finally here, to kind of wrap up a bit, is the errors, right? So we talked about errors and mitigation and of course optimization of these errors. So one thing we also find is, how do we actually characterize these things? How do we determine what these errors are? How do you mitigate against them? How do you actually yourself generate your own noise model? So let's say you want to get into understanding the noises and being able to maybe come up with your own error mitigation technique. So it's with that you have the ability to do that now with a couple of different filters and tools and things that we have here. First of all, with AIR, AIR has a good little feature of simulating a lot of things. Obviously, besides the COSM simulator, state vector simulator, pulse simulators, unitary simulators, other than running those, you can also simulate other things, including noise. So by importing this noise model, you can grab any different types of noise. There are lots of different standard errors. We have a library of different errors. Some of them which I pulled in here, which are for amplitude dampening and phase damping errors. But there's lots of other ones you can pick and choose from. And by selecting these different types of errors, you can apply them to one or many qubits on a particular device and create these noise models. So now when I execute something on a simulator, which simulator we see gives us perfect results, ideal results, because it's an ideal device. By applying these noise models, it can replicate a lot of the noises that we normally see on a quantum system. So by replicating that on a simulator, we can learn to understand them and then apply various different error mitigating techniques to it. So AIR provides us a lot of that stuff with the noise models. With Ignis, this gives us a lot of things, such as things be able to characterize these particular qubits and these errors. You can also do things like determine a quantum volume of a system. So Ignis has a lot of these different components with it that you can use. For our purposes here for this demo, I'm just going to talk about the T1. But as I mentioned, you can get more information on this obviously in the Qiskit API, which goes over details on all of these different circuits that you can run. And these are basically generally just test circuits. So for T1, we're going to start off real simple. In order to do these gates, so first to give an example of what T1 actually tests, is what's called a relaxation error here. It's a decoherence in a sense. So if you think about it, all the qubits start in an initial state, a ground state. In this case, we're calling it ground, the initial state 0, the basis 0 ket, right? And that's when we're pointing it on the North Pole. And in order to move it up to the excited state or the 1 state, we apply, for example, we applied an X gate, and right, and that rotated, if you remember, from 0 to 1. But then, of course, like anything else, when anything that's in an excited state is going to eventually want to come down and relax to the ground state. So over time, that vector is going to, the state of that qubit is going to want to come down and relax in the gate, in the ground state. A good analogy for this for us is that if I give you a 10-pound weight and I ask you to hold it out in front of you with your arm extended, you'll be able to do that without a problem. But if I tell you to hold it and I go away for about an hour or two and I come back, you're probably not going to be holding in that same position, because overall your muscles are going to start straining and your arm's going to want to come back down to rest. So over time, that's the same thing that's happening with this qubit. It's going to be in that excited state for some amount of time, but eventually it's going to just relax down to that grounded state. So in order to test this, we need to do a couple things. One, to really test it, is the same thing. We put it in a 1 state and we leave it in there for some amount of time. And over time, we just start going and just checking to see where it is over time. And eventually somewhere along the line, it's going to come down to a 0 state. So to do that, we want to be able to create these test circuits. So in order to do that manually, if we do that manually, that would take forever. But because we have Ignis and the characterization library, we can do a lot of that stuff automatically. So if we look at this, we'll say, for example, right now we're going to create various different tests. So the first ones I want to do is I want to create 100 tests, separated 12, at a time. So every 12 or so, I want to add another test value, and then I want to shoot it and append larger values, of course. So 200 circuit test, 400, 800, 1,000, 2,000, and 4,000. And I'll show you what this means in a bit. But these are basically the number of gates that we're going to want to apply in between to hold off that time for that gate qubit. The gate time itself is just that, what the gate time is for each identity gate that we're going to apply. And which qubit do we want to test this on? And of course, for simplicity, I'm just putting it on the first qubit, 0, but you can specify any number of qubits here depending on the device or however large a qubit machine you want to run. So here I'm just doing it on the first one. And now we're calling this test circuits function. And with that, we're passing 3 arguments, which we just created here, right? One is a number of gates, and this is an array basically of values. And they're going to start from 1, and you can see them down here. We're going to start from 1, 10, 19, 28, 37. It's going to go all the way up to what we added here, 4,000, which is what we declared here. And then the next one is the gate time, which basically specifies what's the time for each identity gate as it grows. So you can see we set it to 0.1. So you can see as each one grows, this is the time that lapses in between the whole operation. And of course, which qubits you want to apply this to. And of course, we just said, well, 1 qubit, so that's all. So what we're printing out here is just that. So we're going to have each one of these represents a test case. So we have first test case is just going to have 1 identity gate. The next is going to have 10. The next third test is the third circuit is going to have 19. The fourth circuit is going to have 28, et cetera, et cetera. And the last one is going to have 4,000 identity gates. So what that means is this. So our test circuits, just to show you what this is going to look like, it's going to have, in this case, we generated 18 circuits, 18 test circuits. You can see that up here. And the first one, which is the very first one that we're drawing, which we said we had 1 gate. And what that means is how many identity gates. So we know that in order to make this test work, we got to get that first qubit and apply an X gate. In this sense, we're putting it in that excited state. It's in the 1 state here. And then we're going to wait a certain amount of period of time, and then we're going to take a measurement. So here we're taking that period of time to be 1 timestamp, 1 delay time. There's that 0.1 that we calculated here, and that's what this 1 means, is how many identity gates are we waiting here. So think of it as a buffer that's going to just hold that position, and then we're going to it's not an operation, it's just holding it, and then we're going to take a measurement. So if we look at the next gate, right, so this is the first test in the test circuit, which is 0. If we look at the next one, which we saw has 10 gates, and that one you can see has the X gates. We put it in excited state, and then now we're waiting 10 times time steps here, and before we take that measurement, right? So each gate, each number of gates that we're adding, we're just adding that much time in between. And of course, the last one had 4,000. So you can imagine that's good. So you're going to have an X gate and then 4,000 of these identity gates, and then we're doing a measurement. So I didn't want to draw that out because obviously that's going to take up a whole lot of space. So I'm just going to give you an idea here what those test circuits look like. So now we have our test circuit created. We're all done from that perspective. We're prepped. Now we want to be able to run this on a simulator that has some noise, right? So the first thing we want to do is we want to create a noise model. So here we want to create, we're using the T1, which is that damping error, and that's that relaxation error that we saw. So in order to do that, you need to create a couple of variables to create that model. So the damping error is basically, you sets up the T1 time and then your lambda. And your lambda basically expressed by that particular gate time over T1. Our gate time we saw was 0.1. And that's the argument you pass in order to create this damping error. 1 minus lambda, that gives you that noise model, that error. And then once you have an error for that particular one defined, you then create your noise model from error, and then you add a quantum error. And the quantum error you want to add in this case is that amplitude damping error we defined. We're going to apply it to, it's going to then ask you which gate do you want to apply it to. So we're applying it to the identity gates because as you saw, that's the gate that we're using to add the time. So hence each time we use that gate, we want to apply the same damping error on it. And then which qubit will it be applied to? In this case, like I mentioned before, we're just using that qubit 0. So once you have that, now we can run it the same way we ran the circuit before. We're executing it. We're calling that backend system. We're saying the number of shots, just doing something quick here with 200. Then we're gonna execute it on all those test circuits. So the execute function can take a single circuit, but it can also take an array of circuits. So the test circuits that we created, as you saw, were an array of different circuits. So we're running all those on this backend, which is the simulator. But one thing we're going to notice is different, that we're now also adding a noise model to it. So there's a noise model variable, and we're assigning that particular one, that noise model that we created, to that particular circuit. So now when we run this execution, it's going to bring us back those results, but with that noise model in there. So if we look back at the results now, and we look at the first circuit, which remember only had that one identity gate in it, you can see that we get the results we expect. So the circuit first does a next gate rotation. So we're in the 1 state. And then we take a measurement after waiting 1 identity step. So you can see that we have that, and we have a very high probability, right? 99% that it's a 1, which is what we expect, and a very, very small probability of error, right? A little bit of error. Because remember, we did add a damping error in there, so there's going to be something in there. So that's why we see this little 0.01 of 0. But still, it's a very high probability of what we're expecting. Now, if we look at the test circuit of the last one we did, which is the very last one, which is 4,000, has 4,000 gates in it. And in other words, we apply a X rotation on it. So it goes from 0 to 1. We waited some time, and when we take a measurement, we should see a 1. But because we put a very large timestamp on it, or a large time lapse in between, that qubit has completely relaxed back down to the 0 state. You can see here, it's down there by 100%. There's not even a little bit of the 1 left at all. So you can see that over this time that we actually had a relaxation go over some period. So it doesn't sustain that. So that's the error and that damping, that relaxation that applies on that particular qubit. So with that, how do we determine what that particular piece is? So within Qiskit, they have, in Ignis, we have something called a T1 fitter. And this is used to be able to estimate what that T1 time is on that particular circuit. And when we do that, we create that particular fitter, we can then get that information and plot it. And when we plot it, we get that information for that particular, whatever particular qubit. Since we applied it to qubit 0, that's what we're going to check here in the plot. And what that shows us here, you can see, is this sort of a time lapse. So on the x-axis, we have the time in microseconds that we applied. And then the excited state population basically is what state it was in that we're expecting it, that it came in after our test. So you can see at the very beginning, when we put it in the excited state, we took a measurement right away. We got that 1, which was great, and that's what we got. But you can see that as time increases, that particular qubit, now when we measure it, starts to come down. You can see the relaxation starting to dip down here. And it was about after 100 microseconds that this thing had completely relaxed down to 0. And at that point, anytime after that, we're just already in the ground state. So what the fitter does is it not only plots that information for us, but also determines our T1 time, which here I calculated about 14 microseconds, puts you right about here, which is pretty much right about the time where we start going down below, the high 60s as far as probability that we're now low. That because if we're too close to 50%, which means that we're no longer in one state, we're now in sort of almost a superposition state rather than in a one state. And then after some time after that, of course, we're dropping into a completely different state altogether. So this is what it has for the T1. And of course, we can apply the similar thing for a T2, which is dephasing. And this is, in a sense, pretty much the same type of a test. The only difference is we're going to a Hadamard gate as opposed to an X gate, because now for dephasing, we're looking at the rotation around, the particular z-axis of this block sphere, for example, or Q sphere. So by applying a Hadamard gate, we're in between a superposition. Then we're going to wait some time, and then we're going to apply a phase rotation, and then we're going to apply a Hadamard again, and then get a result back. So by doing that, we could do the same way here we did before. We could put the number of identity gates to describe the time difference you want to put in between. So the first one, you saw we only have one. The second one here has 6, and then of course they start to grow and grow as we get larger and larger. And this basically represents that time phase. So after some time, we should be able to have by a certain phase rotation, be at a certain position that we expect to be in. And it'll do that basically oscillating back and forth. So I'll kind of go through these. This is pretty much the same thing that we saw here. In the first test, you could see the first test was we put into a Hadamard, we were superposition, and we made a slight rotation on it, very slightly, but we're still in a sense where if we apply the same rotation to another Hadamard, it should bring us up to the 0, which it does here. So that gives us a 99% chance of getting 0 and a very, very small chance of getting 1, which is exactly what we expect. But now if we look at the very last one, you can see that here we are now right in between 0 and 1. So in other words, when we're in the phasing, in superposition, we're in between phases. When we do phase rotations, we want to be sure that when we do a phase rotation and then we take a measurement, that the system comes back to some state that we know, either 0 or 1. In this case, we should be coming back to 0. But because of the fact that we're between 0 and 1, which means that phase is just kind of flapping in between 0 and 1 so much that we really don't know whether it's in one side of this phase, let's say 0 or pi. It's somewhere dancing in between 0 and pi, and maybe pi over 2, etc. So hence why we have this this difference here. And if we look at the fitter, and that gives you more of a visualization of what we're trying to see here, you can see that when we initialize it, we should get a high probability of 1, but then it comes back and forth to 0. So this should be coming back to 0, 1, 0, 1, 0, 1. But you can see over time, it just starts to end up fluttering here in between 0 and 1. So we kind of lose that state information now between the phases. So our T2 time now says it collapses somewhere around 10 microseconds, which is right about here, which pretty much is right, because right around there, we're now in this sort of 60% probability state, and then getting just smaller and smaller, closer to 50, which gives us that unknown state of like we're in between 1 or 0, or between this sort of detuned phase that we can't really clearly define where we're expecting to see within that qubit. So that's what this sort of kind of illustrates here for T2. This again is dephasing. So first one we saw was relaxation, which is going from 1 to 0, and dephasing is basically the sweeping from 0 to pi, for example. And finally, for mitigating errors. So for measurement error, when you take a measurement, you're reading from that particular qubit. And that qubit is in the particular state, one or the other. But to take a measurement, you have to do quite a lot of things in order to do that. You send an acquisition, you go through an acquisition channel, you send a measurement pulse through a measurement channel, then you're reading in. So there's a lot of components, a lot of things coming in. And of course, maybe the errors that are already introduced within the qubit, et cetera, dephasing, decoherence, et cetera. So when getting these results back, you kind of don't know, you get some noise, you get some errors, and you really want to find a way to lower those errors as much as possible. So that's where Ignis comes in, and part of its mitigation module, it has this complete measurement calibrator and fitter, which is pretty much similar to what we saw earlier with the tests with T1 and T2. You get these, you get a method here to get that complete measurement calibration. You pass the qubits that you want to test this to. In this case, we're going to run, just to try all different measurements, I'm going to run on a simple 5-qubit device. We have 5 qubits, so 0 to 4. So those are the qubits that I want to run the calibration on. So I'm setting the number of qubits in a register, and I'm giving it some label. And so once I run this is going to give us back our measurement calibrations and then the state labels. And the state labels, because we're 5 qubits, that's basically 2 to the n different labels. So we're going to have 32 different labels starting from 0. So if we look at the measurement calibrations coming back for the last one, let's say, so that's basically looking at everything is in the sense in X gate. So calibration means it's looking at all the prepared states between zero, since it's 5 qubits, between 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1. So the second calibration for the 0, 2 would be, have an X gate here and then 0 everywhere else. The next one will have an X here, 0 everywhere else, and the next one will have XX here. So it'll just basically apply that to each one. Just to give you an idea what that would look like is something like this. So this first one would have no gates applied, and just do a measurement. The other one will have an X gate on the first qubit. The next one will have an X gate on the second qubit. So basically, it's going to prepare all of these states. And once it prepares the states, it's then going to run this calibration on it. So if we scroll down here, you can see we've got this running on the back end, no noise, just run it the way it is. You can see we have a prepared state. So what we're doing is we prepare different circuits. We have a state, we're preparing it, and then we're going to take a measurement. So it should just give us back this number. And when we do that and we look at the results from that, we can see we get this nice little matrix here, the calibration matrix, which tells us that the diagonal is what we want because the columns represent the prepared state. So the first one is 0, 0, 0, 1, 1, 0, 1, 1, et cetera, et cetera. And the y-axis here gives us the rows rather gives us the actual measured results. So if I apply here 0, 0, 0 and I measure 0, 0, I get that here. So it's 100%. And this is between 0 and 1, these values. So, but if I apply, let's say I measure it to the 0 state, but I get back 0, 0, and let's say over here I get back 0, 1, then this is going to read 0.5 and 0.5 because meaning I measure this one time, I measure this one time, and means I have a 50-50 probability there that I got back that result for that prepared state. But because there's no errors here, this is just running on a simulator, we get back this nice perfect thing. And to visualize that here, we can see that here. These are all the measured states that we measured. So if I measured zeros and the prepared state, of course, is very small, so all these numbers are hard to read. But the prepared state here will be for all zeros and all zeros, so we got that here, right? So this is just a visual representation of what you're seeing here. Now, if we were to add a noise model to this simulator, and again, we're doing it for all the 5 qubits, or each qubit is going to add in, we're going to add these readout errors, and we're applying this particular values for those types of errors that we're going to get. And that becomes our noise model that we're creating. And now if I rerun this particular circuit, but this time adding that noise model, so in other words, it's not going to come out perfectly here. So my prepared state are not always going to match my measured state, which is what we see here. What we'll get then instead, as you can see, is from this results, you can see now we have values. Our diagonals aren't perfectly one. They're all different values. And you can see here, there's different values and different points on the outside of here. And those, of course, are the errors. If we look at the visualization, you can see here for the prepared state of all zeros, we get a lot of results back from all zeros as well. But you can see there's a few times where other results came back. So here's 0, 0, 1, 0, 0. This one is 0, 1, 0, 0, et cetera, et cetera. So these all indicate that there is some, even though we prepared and we're expecting these states, we're getting some errors. We're getting some different errors in information from here. So based on this result and this noise, what the calibration fitter does in this sense is understands, it models that particular information. And I'm going to scroll down here. And what it will do then is it'll apply a particular filter rather to that to filter those particular results. So here what I've done is I created a simple circuit similar to what we've done before, except this time I'm entangling everything together here from a 5 qubit system. And then what I'm going to do is I'm going to run it on a backend, on an actual backend system. So you can see here we're running it on at the time when I ran this, it was on IBM QRN. So it's running on an actual backend system. And then we get back our results. We execute it then, and we get back here, we call it noisy counts. That's the result. That's the raw data coming back, meaning we haven't applied any error mitigation at all. That's what we have back here. And what I'm doing though is I'm now creating this filter, this measurement filter based on that fitter that we created earlier, based on the prepared states and what the measurement states were, et cetera. And now I'm going to apply those results that we got back into this particular measurement filter. And then this will give us something we see that are the filtered results. So we have noisy counts, which is the raw data, and filtered results, which have been filtered through that particular measurement calibration tool. And then now if we look at the filtered result counts, we look at it, we can see a much different thing. So if we look at the noisy counts, on the histogram, we can see we have all zeros and all ones, which are where we expect, but we still see some noise here. In other words, right, we're supposed to expect, because of that state, all zeros and all ones, but we still see a little bit of noise. So that's the noisy counts. That's the raw data coming back. But if we look at now the filtered counts, you can see that it filtered out pretty much everything, right? So now we have what we expected back, 0 zeros and all ones, and then everything else was zeroed out. So we had no noise of any kind in this sense, right? So that helps us a lot of those. And you can, of course, not only apply with all of them, you can apply into a subset of those particular type of circuits. So here we did the same thing. And here, when we got back the results, I have one that shows the mitigated results, which is after we applied the filter. And here we have the raw counts, which came back as is. So when you look at the results here now, and I put these together side by side so you can see them, the raw data, which was not cleaned, is in blue. So here we're using just 2 qubits. So you can see the errors a bit more here. And then once we mitigated those, that comes in red, you can see it completely removed those errors and then applied the proper amplitudes here with those results. So, mitigating these types of errors and the measurements and everything that you get back are a good way to clean up your data. Now, they're not perfect because some also depends on the device, because this is partially on measurement data and noise models that we created, but you might get other different types of noise models, or noise rather, that comes in. So you'll have to try to work on, depth, for example, and dephasing, decoherence. If that's noisy, it doesn't matter how your measurements are coming out. It just means that those qubits are pretty much at a state that's very difficult to clean up after. But this at least helps out some in that aspect. Right. So with that actually concludes the stuff that I covered here. Let me go back over here and check the chat, because I think there were some questions there maybe. And
sure. First, let me just say thank you very much, Robert. That was a fantastic and thorough introduction to QuizKit. The comments were very positive. I know people enjoyed it very much, and at least one person ordered the book while you were doing your presentation. So
that's great. Okay.
In view of the time, maybe we could have just 1 or 2 questions.
Sure.
I think Faisal, you asked a question.
Yes, Mark. Hi. Thank you. My question was with respect to, well, actually I had 2 questions, but I'll just ask the first one, because I think near the end, Robert did address the second question. So my first question was, how is the IBM Q different than a classical probabilistic computer or processor, given that several runs have to be made to decide empirically what the observed state is?
Right. So let me see if I can understand. So if we're running, so for example, you talk about the shots when we do these shots, right? Yeah. So the difference in a sense is, let's assume I have a 1,000 bit, 1,000 qubit, operation I want to run, and I want to take those simulations, and I'm looking for a 1,000 bit number out of that. So if I run something like Grover's algorithm on this, on a classical system, if you get a 1,000 bit system, you have to iterate through all those different, right, 2 to the 1,000 in a sense, right, to be able to find that one value. With a quantum system, if you're using, for example, Grover's algorithm to solve this, you can run that same Grover's operation and in the quantum parallelism, right? Everything's in a superposition, and you run through it. If you run it 100 times, let's say I say shots equals 100, and of course, if it's a very clean device and not noisy, etc., I can probably only run it 100 times or 50 times or 1,000 times, and that's it. And that'll give me my results, similar to what you'll see here, for example. So, the shots is just to give you that probabilistic results, but it's not directly related or proportional to the number of qubits or bits or qubits. And if you're going to read them back to the same number of bits, that's what your results will be back. Versus on a classic system, if I have a 5-bit, search I'm running 2 to the 5, so 32 different iterations if it's the last number, let's say. But if it's a 1,000 bit number, then I have to go through it very, 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 each one, it might take obviously a very long time. Where on a quantum system, I have a 1,000 qubit or 1,000,000 qubits, and I run them 100 shots, that's it, I have my result back, right? So it's not directly related to the qubit count. So I hope that answers your question there.
It does. Thank you so much, Robert. Excellent presentation, by the way. Thank you.
Thank you very much. Appreciate it.
Thank you. And I think we can have one final question from Barry Bird.
Yeah, hi. I wonder if you've seen the Microsoft Q Sharp system, and if you have any words of comparison between that and Qiskit. and the IBM Quantum Experience?
Yeah, I honestly haven't. To be honest, I haven't really. I know we use stuff from Ticket, right? So for CQC's pieces, but when I joined Quantum System, it was directly into IBM Quantum, so I was just exposed to Qiskit and the work. So that alone took me quite a bit of time to get it to to get up to speed with it. At the time when I started, right now the Qiskit community has a lot of really great content and things to really help you get started. When I started, it was really difficult, but it had a good community, so I just found it easy to use. I've seen obviously tutorials and things that use Circ and YouTube, etc., and other different platforms, even on MATLAB. I was looking up. I'm right now studying neuroinformatics, and I was looking at MATLAB, and they have a quantum toolkit. So it's interesting that there's a lot of things, but of course, the one thing that drew me here was because I had access to an actual device, which I think was for me the one thing I really kept with it, was because it's one thing on, from a purely quantum computational perspective, I'm creating an algorithm, etc. It's that's almost agnostic to what I'm running on. It's just I'm just creating some algorithm to kind of do some work, and that's it, to solve a problem I'm trying to look at. The advent that Qiskit offered me was that I can actually do it, one, obviously on an actual device, and two, I can actually, through various different things here, actually program directly onto that particular device as well. So if there's some noise, I can, like I was showing you here, I can actually apply different modules that helps me get better results, et cetera. So hence it helps my algorithm that I'm trying to develop, et cetera. In this case, I was doing stuff on quantum image processing. So it just gave me a lot of features that are not just simulated, because there's simulators everywhere. This one actually gives me that ability to be able to run them on an actual device and understand the hardware, and like I mentioned here, optimizations and these kind of things, which kind of gives it a little bit of, for me, it was interesting. I hope that answers your question there.
Yeah, thank you.
Yep.
Super. So thank you so much again, Robert. And again, there's a discount code I posted again for those of you who missed it the first time.
Yeah, and I think I promised, and I want to make sure I live up to a promise. I'm most of the posts for this, I promised I was going to give away a copy of the book.
Yes.
So I was trying to figure out how to best do that. So I think probably a quick and easy way to do it here, because usually if it's in person, I just ask a question, somebody raise their hand. If they get it, they get the book. But us being virtual, I figure what I can do is I'll ask a question, and the first person to answer it on the chat, I will then, I guess once I pick your name, just private message me on the chat before we disconnect, or maybe just private message me if you want, where you want me to send the book. I'll sign it and send it over to you, so that won't be a problem. So I figure I can do that now if that's okay, Mark.
Yes. Yeah.
So all right. So all right. So we covered a lot of different topics here, and so one of the questions that I figured I'd ask is, there are I'm trying to figure out what's the best way to ask it, where it's you won't, so don't get too wordy with the answer. Just trying to give you it real quick. There are 4 different elements in Qiskit. Do you know what they are? And if you could list all 4, the first one to list all 4 would be, we'll get the book. So let's see. What are the 4 elements of Qiskit? Oh, wow. Okay, that was quick. So Ramya, very good. Awesome. Terra, air, ignis, and aqua. Yeah, so those are 4 elements in this sense. Is and they're all different by how their uses as far as what you need. Like I mentioned before, ignis here talked about the air was on simulator, Terra on the components, and aqua, of course, is these algorithms that we're using. So Ramya, congratulations. If you want, you can go ahead and private message me on this. Just send me an address where you want me to ship the book, and I'll be more than happy to do that. And for everybody else, yeah, as Mark mentioned, there's a there's a discount code in the chat. The Amazon link is for those that are in the US, for US residents, US addresses, and in those and outside of the US, there's the Pact Publisher link that still gives you the same discount. I guess it's just how they apply the discounts for people outside the US. Shipping, I guess, I don't know, or where they ship it from. So yeah, so with that, Mark, I will, let me actually get, yeah, so with that, Mark, I'll pass it back to you.
Fantastic. So thank you everyone again, and I will see you all in 2 weeks.